Hello, everyone. My name is Qing Chen. I'm from University of Zurich. I will talk about our work on connectivity queries. Here is a plan for my talk. The main focus is SD and the D tree. So first of all, let me warm you up. The input graph are undirected, simple, and dynamic. So simple means there are no loops in the graph. Dynamic means we can insert and delete vertices and edges. For connectivity query, and it defines that given two querying vertices U and V, if there exists a path between U and V, the query returns true, otherwise returns false. Example, 3, 9 here, since they are belongs to different components, they are disconnected, query returns false. Since in the dynamic graphs, we can insert edges. So we insert an edge 1, 6. So 3 is connected to none. And we can also delete this edge. And 3 is disconnected to none. And actually, there are also there are two operations that are not very important because inserting isolated vertices and deleting isolated vertices can be easily handled. So now in this talk, I will focus on the inserting edges and deleting edges. As you can see here in dynamic graphs, the connectivity queries for two given vertices can change from time to time. If the graphs are large, so the challenge is how we compute a connectivity query as efficient as possible. So we look at the exist work in practice and in theory. So in our community, so graphs in the existing work have no more than 40 million edges. So in real world, graph can easily condense billions of edges. So in theory, unfortunately, no experimental evaluation and for all theory work. And what's more, the theory work optimized for worst case scenarios. I will explain the worst case scenarios in next 2 slides. So we are motivated to develop a scalable solution for connectivity queries on dynamic graphs. So here's the problem definition. Find an efficiently maintainable data structure for fully dynamic graphs that, on average, answers connectivity query efficiently. So efficiently maintainable means we maintain the data structure almost on the fly. And we have an assumption here, queries are uniformly distributed. Developing workload-aware approach is our future work. So we also assume that graphs have small diameters. I will explain why we have such assumption in the next slides. You may know that the graph data repository Connect. So it investigates 1,324 graphs, real-world graphs in 24 categories, and it shows that 90% of the real-world graphs have small diameters. More specifically, the diameters are less than 17. So by definition, diameter is the length of the longest shortest path in the graph. And the worst, all the theory work optimize the 10% of the graph that have large diameters. We argue that graphs with small diameters are more frequent in the real world. And what is our technique? We are leveraging spanning tree. So given a graph with two components, we construct each spanning tree for each component. So here is a spanning forest of two spanning tree. So connectivity queries on spanning tree is that given two query vertices U and V, if they have a same root, the connectivity query returns true, otherwise returns false. So example, so for 2, so the red node are the root of the spanning tree. It goes to the root, here the root is 1, for 10 it goes to the root, so 9 is the root of spanning tree contains 10. So 2 and 10, they are in different spanning tree, different components, query returns false. As you can see here, answering connectivity query in spanning tree is simplified. Traversing to the roots instead of traversing all vertices on the graph on connected components. And we have a cool technique here. However, there are challenges. Given a graph, there can be exponential number of spanning trees, but not all spanning trees are good. We are looking for good spanning trees. Good spanning trees for connectivity queries are flat. So in a flat and shallow tree, the nodes have smaller distance to the roots for queries. So more formally, we propose a new metric, which is called sum of distance between the root and the node. So more formally, by definition, we have a spanning tree here with the root R, sum of distance, SD, calculate the distance between the root and all nodes in the spanning tree. You can see one example here. And the main takeaway is small SD, small average distance to the root, fast queries. I will repeat this. And there exists one optimal tree that gives optimal average query performance, which is BFS tree. Because BFS on the graph give us shortest distance. We cannot do better than this. So there are so many breadth-first trees, and we need to select the one with minimum distance, minimum SD, and this is the optimal one. So the optimal one has optimal average query performance. So for the dynamic graphs, we need to run breadth-first search, BFS over all vertices for every single insertion and deletion to compute optimal. If we do this on graph with millions of edges, it takes hours, which means computing the optimal solution is too slow to be used in practice. We need to do it faster. So the D tree comes. So D tree is short for dynamic spanning tree, and that employs very efficient heuristic to manage small SD. So there are 4 operations. Since there are 2 different kinds of edges, tree edge and non-tree edge, and the 2 operations on the graph, insertion and deletion. So in total, we have 4 updates. And we will look at inserting non-tree edges due to the time limit. We look at detail here in this one. So non-tree edge, which means this edge is not on the spanning tree. So imagine we have a graph which is not drawn here. We have spanning tree here so far, and we insert an edge 5, 8 in the graph. So here's a dotted line here. And what happened here? The nodes in the green part, in the green subtree, which are 4, 5, 6, they have a shortcut to the root, which is through 8. So the heuristic flatten the tree. So with link cut operation, we cut the tree edge 3, 4 and turns it to a non-tree edge. We attach 5 as a child of 8. So 5, 8 become a tree edge. So as you can see here, some distance it decreases. The heuristic does not stop here. It continues. So when 5 is attached to 8, we traverse to the root. We look at the size of subtree rooted at 8. Number of vertices in the subtree rooted at 8. It contains more than half a node of the whole spanning tree. So we make 8 as a root. 8 has more than half size. So far 8 is the best root, and sum of distance it decreases. Actually, it's the smallest. So in general, the best root gives us smallest distance for a given spanning tree. So by definition, the best root, which means no children have more than half the size. So which means when we find the best root, we only look at the size, number of vertices in the subtree rooted at that node. And it is fast and efficient to compute, which makes our heuristic very efficient. And due to the time limit, I will briefly walk you through the other 3 updates operations: deleting non-tree edge, constant runtime in D tree, check. Inserting tree edges. So in general, it's D tree attach small tree to the larger tree. which is efficient, and deleting tree edges, which is the most complicated. So in the spanning tree, we delete any edge. So one tree is split into two. So in D tree, split into two, and one is large, that contains more vertices. The other one is small in terms of size. So the D tree, what D tree do is, the most expensive operation is traverse the small tree and to find if there exists one replacement edge to reconnect the two split tree. So the cost is traversing the node in the small tree. So the size of small tree matters. So actually SD optimize for the cost because SD minimizes the size for the small tree. So here we have one simple metric, SD. It optimizes average query performance and the most complicated operation, which is deleting tree edge for the maintenance at the same time, which is super cool. And next, I will show you the experimental evaluation. So here's the setup. Since the graph is changing all the time, we set 100 uniformly distributed testing points through the time span. And at each testing point, we suspend the update. We run queries. For small graphs, we run all pair of queries for all pair of vertices. For large graphs, we run 50 mini queries. And we show here, for example, we show one small graph to show how efficient our heuristics in D tree is. And we also show the scalability of the approach. And as you can see here for SD, so this is the black triangle is the optimal. We can afford to compute for small graphs. So as you can see here, D tree is very close to the optimal. And for the large graphs, Stack Overflow, volatile tree, and optimal tree does not scale to large graph. D tree is always the best. And for query, it's not surprising because query is highly strongly correlated to SD. And you see here, we can draw almost the same conclusion. In small graphs, D tree is fairly close to the optimal. On large graph, D tree is the best. And for maintenance, we show the result for 4 different updates. D tree is always the best. And more specifically, D tree can be up to 50 times faster than the worst case algorithms, HK, which is short for Hinziger-King. And on our largest graph, which is Semantic Scholar with 8 billion edges, the worst case algorithm HK cannot finish the workload in 14 days. Our D tree is always good. So to conclude, we propose a new metric, SD. For connectivity queries, SD is different from balancing the tree. And the main takeaway, small SD, faster queries. And we also propose the data structure that employs efficient heuristics to maintain small SD. And for future work, so one limitation for D tree is that D tree does not work well for graph with large diameter. We are working on this. We're also making D tree workload aware. So thanks very much for your time. I'm open for questions.